Welcome to this lecture series in group theory. We are starting a new module in which we will finally introduce groups. In the previous module, we looked at some number theory, some linear algebra. In particular, we introduced finite fields and looked at some applications. In this lecture, I want to motivate the notion of a group. We will not give a formal definition here, but we are trying to get to a formal definition. What is a group is something that comes after why is a group. We are trying to answer the question why is a group. All right, so let's get started. So a group, or the notion of the group, is about symmetries. And to illustrate the idea, let us look at a very simple example. Let's talk about the symmetries of an equilateral triangle. So I have drawn an equilateral triangle here, and if I ask you what are the symmetries of it, you might say that clockwise rotation by 120 degrees is a symmetry, for instance. So let me give a sort of an informal definition for a symmetry, at least for this particular object, and then we will say something about the general definition of a symmetry later, maybe in the next lecture. That is what really a group is all about. So for us, for this particular lecture, and for this particular triangle, which I'll denote by T, a symmetry in double quotes, because we are not formally defining it, a symmetry of T is a rigid motion. Now, what is rigid motion? So a rigid motion is, you can think of it as a transformation of this triangle where you do not distort any distances. So for instance, clockwise rotation by 120 degrees is a rigid motion. It is not going to change the distances between any 2 points on this triangle, right? So just your intuitive notion of a rigid motion is sufficient to follow this lecture. So a symmetry of the triangle T is this triangle, is a rigid motion which preserves T as a set. We are not asking that the rigid motion preserve T pointwise, because that would be foolish. If I talk about a transformation which preserves this pointwise, that is basically the transformation which does nothing. It's the identity transformation. We also want to talk about non-trivial symmetries. The do-nothing transformation is also a symmetry because it also is a rigid motion which doesn't change any, I mean, if the word symmetry means anything, the do-nothing transformation should qualify as a symmetry. So that is a symmetry, but we also want to talk about non-trivial symmetries. So we are not asking the rigid motion to preserve this pointwise. We are only asking it to be preserved as a set. For instance, the clockwise 120 degree rotation doesn't preserve the top vertex, vertex's position. It takes the top vertex to the bottom, to this right vertex, and takes the right vertex to the left vertex. Although, if someone was not in the room and you applied this clockwise 120 degree rotation, that person wouldn't know that you have actually applied it after he enters the room, right? Because after 120 degree rotation, the triangle looks exactly the same. So that is what I mean by preserving T as a set. Okay, I hope these notions are intuitively clear. Okay, and now to witness the symmetries properly, we would like to assign colors to the vertices. So now I have colored the top as orange, right as blue, and left as red. And here, when you apply 120 degree clockwise rotation, the orange will come here, the blue will come here, and the red will come on top. And that will kind of show us what symmetry was applied. So this is just for our understanding. The original triangle was this. So now let us get started with at least one symmetry, namely the clockwise 120 degree rotation. And here I've drawn a figure. This is, you can think of as our starting configuration. If I apply clockwise 120 degree rotation, I will arrive at this configuration. The red vertex will come on top, orange will come on right, and blue will come on left, and that is exactly what you see here. You once more apply clockwise 120 degree rotation, you'll see this configuration, right? You can just tally. This comes on the right side, orange comes on the left side, blue comes on top, right? But now if you do one more time, if you apply clockwise 120 degree rotation one more time, you land back to the initial configuration. Okay, so this is a very simple observation, which was not really necessary in the sense that it is nothing surprising. You already knew this, even without realizing that you knew this. But still, I want to emphasize this. Something has happened which we want to capture algebraically. So let me denote by R the clockwise 120-degree rotation. Think of symmetries as transformations applied to a configuration. R is your abstract symbol which is denoting the clockwise 120-degree rotation. It can apply to any configuration. You can kind of apply this to this configuration or that configuration or that configuration. If you apply it to this configuration, you get this configuration. Apply it to this configuration, you get this configuration. So you can think of symmetries as being acting on configurations of the triangle. All right, and we already observed something, that if you apply the clockwise 120 rotation 3 times, you get the do nothing transformation or the do nothing symmetry. Right, that's exactly what we see here. Apply, you get back the original. Apply, you get back the original, and so on. And this equation, if you can call it an equation, this equation we will write like this. So the do nothing transformation is denoted by E. And here I am kind of borrowing from high school algebra. Just think of R as your variable, as you call it in high school. If you multiply x with x with x 3 times, you get x cubed. Similarly, if you multiply r with r 3 times, you get r cubed. Right? So the geometric observation that applying the clockwise 120 rotation 3 times in succession produces the do nothing symmetry, or is as good as doing nothing, is now captured in this equation. Okay? Also, if we think about it, the r applied 2 times in succession is anti-clockwise 120-degree rotation. Right? If you apply R 2 times, you're getting this configuration, which is as good as rotating in the anti-clockwise direction by 120 degrees. The orange will come to the left, red will go to the right, blue will come on top. That is what you see here. So this is also something that we see, but this we can write, or we can kind of borrow from the first equation. We can write it like this. So this I'm writing as R inverse. The anti-clockwise 120 rotation is kind of the inverse of the clockwise 120 rotation. Clearly, if you apply clockwise 120 and then anti-clockwise 120, you get back the original thing. So it makes sense to call it the inverse of clockwise 120, right? And this we are abbreviating as R square. But this equation and that equation are the same things, right? Just high school algebra, if you are willing to play along. If you were in high school, you can immediately from this write that. So in some sense, this was no new information. So far, everything has been captured here. Okay, something is happening. We are not there yet. But now you may ask, what about reflections? Suppose I want to reflect about this vertical line. If I do that, the configuration that I will get is the following. The configuration after reflection would be the red would move to the right and blue would move to the left, and orange will remain where it is. This is what you get if you apply reflection about the vertical line. And this configuration is nowhere to be found amongst the 3 that we already have. You cannot apply rotations to get a reflection. Basically, that is what is something that we observe here. Okay? So we need to expand our set of configurations to capture the vertical reflection, or the reflection about the vertical line. And that is what we do in the next slide. So this was our original thing. This was just the rotation diagram. Now you are reflecting about the vertical line. This dotted line is denoting the reflection about the vertical line. And I haven't drawn any arrows here because if you apply reflection twice, you get back the original. So if you want, you can draw arrows on both ends or no arrows at all. Right? So if you apply the vertical line, the reflection about the vertical line to this particular configuration, you will come here. Similarly, you can check if you apply the vertical line reflection for this configuration or on this configuration, you get here. And similarly, this one. Further, now if you apply clockwise and clockwise 120 rotation, you're going this way to get this configuration. Right? Just tally with the figure. If you apply clockwise 120 rotation here, the orange comes on the right side as it does, the blue comes on top as it does, the red comes on the left as it does. So even though this cycle is going anti-clockwise, that is just diagrammatic. Really this arrow is capturing clockwise 120 rotation. So as in the previous slide, the bold arrows are capturing clockwise 120 rotation. So that is maintained. Some extra thing has happened that dotted lines are denoting now the reflection about the vertical line. So now we need to introduce some more algebra. So the symbol R was used to denote rotation by 120 degrees in the clockwise sense. Let us use S to denote reflection about the vertical line. And we have already observed that R cube is E. E was again the do nothing transformation. But what about this guy? Clearly, if you apply reflection twice, you get back the original thing. So a similar algebraic capturing of this geometric phenomena or phenomenon would be this equation, right? If you apply, maybe I'll be more detailed. If you apply S 2 times in succession, you get the do nothing transformation, which we can abbreviate as S squared equals identity. Or in other words, S is its own inverse, right? But still, it is unclear how R and S behave amongst each other. R has its own world, S has its own world, but there is some relationship between the two. They are not, in some sense, independent symbols. For example, suppose you first apply rotation by 120 degree clockwise, and then you reflect about the vertical line. Or you first reflect about the vertical line, and then go anti-clockwise 120 degrees. You end up at the same configuration. So it shows that first you apply rotation and then reflection. I'm just referring to this as rotation, but this is rotation by 120 degrees clockwise, etc. So first you apply rotation and then reflection. That is same as first you reflect and then rotate anti-clockwise. So that means first you reflect and rotate anti-clockwise. Now, one thing I should mention very emphatically is that when we write this, we may read it as SR, but really you should think of it as R first, S later. This is just like the function composition notation. When we write f composed with g, even though we read it from left to right, f composed with g, but when you feed it x, the consumption starts happening from right to left. First g eats x, and then the output is eaten by f. Similarly, you should think of this thing, when I write SR, you should think of this as something that consumes a configuration. Then R eats that configuration, outputs some configuration, and then the resulting configuration is eaten by S. So this is to be thought of as a sequence of symmetries applied in succession, where the right one acts first, and then the next one, and then the next one. All right, so we just noticed that this is true. So let us add that to our list of laws, and now we can move ahead. Maybe I want to say one more thing, one more very important thing. So here we have been able to capture the reflection about the vertical line and rotations by 120 degrees clockwise or anti-clockwise. What about reflection about a line like this? Have we captured that? Because that is also a symmetry that we want to talk about. But what is reflection about this line? A reflection about this line will switch the orange with blue and keep red as the same. But such a configuration is already available here. That configuration is here. And in fact, you can see that if you reflect and then rotate, you get there. So reflection about this line can be seen as the composition of first you reflect vertically and then you rotate. Similarly, you can capture reflection about this line. So no new symmetries will occur. We can agree that rotation by 120 degree, etc., all the rotations have already been captured and all the reflections have also been captured. We only made this diagram with reflection about the vertical line in mind, but by composing rotations and reflections about the vertical line, you can obtain any reflection. So that's very nice. So we can agree that this diagram doesn't need any more expanding. This is capturing all the symmetries of the equilateral triangle, even though we did not define what is a symmetry very precisely. Okay, so now we can move ahead and that will kind of finish the motivation part. So we just saw that we have these three laws amongst rotation by 120 degree clockwise and reflection about the vertical line. All right. But now suppose somebody asks us the question, what is the net effect of this thing? Meaning first you apply S, then you rotate 4 times 120 degree clockwise, then you rotate anti-clockwise 120 degree and so on and so on. What will be the resulting configuration? Now one can find out what is the resulting configuration by diagram chasing. So here we have the entire diagram with us. Let us chase out and see what happens. First we apply S, then we 4 times rotate clockwise 120 degree. So 1, 2, 3, 4. So we land here. Then we rotate anti-clockwise 120 degree. So we go here, then reflect. Then you rotate clockwise 120 degree. Then you reflect. And then you go clockwise 120 degree 2 times. So this and that. Sorry, no, not that. This and that. So you will come here. Right, finally, this when we were doing this, we were here and we were to do clockwise 120 degree and that would go this way. Right? So just verify that if you apply these things in succession, you will land here if you start here. But using these laws, we could have just computed it. This problem is a geometric problem. We are asking what happens if we take our triangle and apply all these transformations in succession. That's really a problem of geometry. But after doing this symbolic nonsense, we can, in some sense, just compute it as if it were a problem in algebra, right? So let's just play along and compute this according to these laws. I'm not trying to say that everything should make sense right now. You may not be following fully as to what's going on, but let's just play along and see what happens. So we want to kind of compute out what this is. I'll just hack away here itself. Right. So here I see an r to the power 4. Now r to the 3 was the identity, meaning the do nothing. So r to the power 4 is r. As we can also see from here, r is just basically r, right? So instead of r to the power 4, I will just write an r there. So some simplification has happened. Now we see r inverse going in succession with r. So they basically cancel out. They are together basically do nothing operation. So I can forget about that. Now this s and s together are s square, but s square is also do nothing. S square is do nothing, so I can erase that. And now finally, we have SR with us, or we are more comfortable with RS, so let's play with RS. So we have R square S written over here, but that we will write as follows. We will write it as R R S R, and this RS in the middle we will write as SR inverse. Right, just this thing we have written like that. But now these two things, they kill each other, so that is gone. So we see that the result is just RS, which means what? Which means first you apply S and then R. First you apply S and then R, and you land there. So this problem of geometry, which required us to visualize and whatnot, once you write down its laws, the laws of its symmetries, you can just compute at it like usual algebra. And that is the idea of a group. A group is supposed to be the collection of all the symmetries of some object. That object is hidden from us. Here, this set of symmetries was arrived at by taking this particular object and its symmetries in consideration. But really, as we saw, you can forget about all of this pictorial way of looking at it. You can capture all the symmetries in just this symbolic world. So a group is supposed to be the set of symmetries of some object. And symmetries better satisfy certain laws. If you apply two symmetries in succession, you should get a symmetry. Whatever symmetry means, it should satisfy the following simple intuitive fact, that two symmetries applied in succession is a compound symmetry or just another symmetry. Just like if you apply S and then you apply R, it is another symmetry which is nothing but reflection by this particular line, right? So application of two symmetries in succession is another symmetry. Also, symmetries should come associatively or obey the associative law, meaning when I'm given something like this, it doesn't matter how I bracket this. I might bracket things like that or some other way, meaning I can club symmetries together in whatever way I want. Of course, I'm not allowed to arbitrarily shuffle them because the law of shuffling is a bit complicated. This is not the same as saying RS is SR, right? So you cannot, sorry, what I've written. This is not the same as saying RS is SR, but still some law is available to us. In general, we are not allowed to shuffle any which way. We can bracket any which way we like, that is associativity, but we cannot shuffle any which way. So this is just a basic thing, right? If you are given a bunch of symmetries which you apply in succession, it doesn't matter how you club them. That is intuitively appealing. So that axiom should be there. Further, every symmetry should admit an inverse. Just like if you rotate by 120 degree clockwise, you can nullify its effect by rotating back 120 degree anticlockwise. So every symmetry admits an inverse symmetry, something that kills its effect. For reflection here, we saw that reflection itself kills its effect. So to wrap it up, symmetries must obey the associativity law, symmetries must admit inverses, and there must be a do-nothing symmetry. Like do-nothing should always be counted as a symmetry, right? And that is something that we kind of started with. So I hope this motivates the notion of a group. And in the next lecture, we will give a formal definition and then develop the abstract theory. All right, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.